A typhoon hits without warning. A ferry fully loaded with passengers and cargo rolls in the churning waves of the Tsugaru Strait. The captain tries to turn back. It is already too late. The vessel capsizes in darkness. Over 1,100 people drown in a single night. And somewhere in Tokyo, engineers stare at a map of the sea and ask a question that will define the next half-century of Japanese infrastructure. What if we go underneath it? Welcome back to the channel. Today we are talking about one of the most extraordinary feats of underground engineering ever attempted in the entire history of human civilization. This is the story of the Seikan Tunnel, Japan undersea passage connecting the islands of Honshu and Hokkaido. Buried deep beneath one of the most violent and unpredictable stretches of ocean on the planet. A tunnel that took 24 years to build, a tunnel that cost approximately 690 billion yen, a tunnel that nearly drowned its own workers twice during construction. A tunnel that, when it finally opened in 1988, was the longest railway tunnel on the face of the Earth. And a tunnel that today carries Shinkansen bullet trains at 260 kilometers per HR through a passage carved into the living rock of the sea floor. 240 meters below the surface of the sea. This is not just a tunnel, it is not just a piece of infrastructure dug into rock by machines. It is the physical embodiment of a nation's refusal to accept that geography should determine destiny. It is 53.85 kilometers of determination, precision, pain, and brilliance. Carved through fractured volcanic rock, through fault zones, through water-saturated ground that fought back at every single step, in conditions that no tunnel had ever faced before, and that no tunnel engineer had ever encountered at this scale. Imagine it for a moment. You are standing on the seafloor of the Tsugaru Strait. Around you, the weight of 240 meters of ocean presses down in every direction. The rock above you is not solid granite. It is broken, ancient, volcanic, cracked by fault lines that run across your path, soaked by seawater that has been filtering through it for millions of years, ready to collapse if disturbed by too much vibration or too aggressive a blast, and 100 meters below the seafloor itself. In a tube barely large enough for 2 trains to pass, a Shinkansen is accelerating toward 260 kilometers per hour. That is what they built. That is where they built it. And this is how. But before we go underground, make sure you subscribe to the channel if you haven't already. Hit the bell icon so you don't miss our next video. And stay with us until the end. Because what happened in May of 1976, deep beneath the Tsugaru Strait, when approximately 70 million liters of seawater exploded into the tunnel workings, you are going to want to hear how they survived it and how they kept going. At first, there was only the strait. No tunnel, no bore, no passage of any kind. Just 23 kilometers of cold, churning seawater between 2 islands that Japan had been struggling to connect reliably for generations. The Tsugaru Strait is not calm ocean. It is not a gentle coastal channel. It is one of the most hydrologically violent bodies of water in the entire Japanese archipelago, whipped by powerful currents flowing between the Pacific Ocean and the Sea of Japan, hammered by typhoons that arrive with little warning, gripped by sea fog so dense it grounds ferries for days at a time. Ferries crossed it because there was no other option. And for decades, that was considered acceptable. Until one night in September 1954, it catastrophically was not. The Tiamaru was a standard passenger and railway ferry, one of many making the regular crossing between Honshu and Hokkaido. On the evening of the 26th of September 1954, despite the approach of Typhoon Marie, the vessel departed. The storm was severe. The sea state was dangerous, but departures had been made in bad weather before. This time, the Tiamaru never arrived. The vessel was overwhelmed, rolled, and sank in the Tsugaru Strait. More than 1,150 people lost their lives in a single night. It remains one of the most devastating maritime disasters in Japanese history. The national shock was profound. And within months, the Japanese government had begun taking seriously what had previously seemed like the fantasy of engineers, a tunnel under the sea. If you build a bridge, the Tsugaru Strait destroys it. The typhoon wind speeds. The wave heights generated by the interaction of 2 major bodies of water, The frequency of severe storms throughout the autumn season, the length of the crossing a bridge across the Tsugaru Strait would face forces that no bridge of that era could reliably withstand at that span. If you continue to rely on ferries, people die when the next storm arrives. Those are the two options nature offers. Neither was acceptable to a nation that had just watched over 1,000 of its citizens drown in peacetime, so the engineers chose a third option. Go under. Go so far under that the weather becomes irrelevant, that the waves become irrelevant, that the storm that capsizes ships on the surface is completely invisible, completely inaudible, completely without consequence to the trains passing silently through the rock beneath the seafloor. The solution was not simple. This was not a case of choosing a design from a catalog. No tunnel of this length had ever been driven under the sea. No one had ever bored through geology like this at this depth. No existing engineering playbook covered the situation. The solution had to be invented as it was executed. And it began not with drilling, but with years of not knowing construction was formally authorized and began in 1964. But the first years of work were not excavation, they were investigation, because the geology beneath the Tsugaru Strait, the rock, the fractures, the water pressures, the fault zones, had to be understood before a single blast could be fired. Survey ships conducted seismic profiling of the seabed. Drill rigs on those ships lowered core barrels through the water column and into the rock below, bringing back cylinders of material from the intended tunnel horizon. Geologists analyzed these cores under microscopes, measured their strength, measured their permeability, measured their fracture frequency, and what they found was deeply alarming. The rock beneath the Tsugaru Strait is predominantly neogene volcanic material, heavily altered, geologically ancient rock laid down during a period of intense volcanic and tectonic activity. It is not the strong, clean granite that tunnel engineers dream of. It is a complex mixture of tuffite, mudstone, sandstone, and breccia cut by multiple fault zones that run roughly perpendicular to the planned tunnel alignment. These faults are not thin hairline cracks. They are zones of crushed, sheared, decomposed rock, sometimes meters wide, saturated with seawater held under pressure by the weight of the ocean above. The stronger rock between the faults is still heavily jointed and fractured. Almost none of it could be described as self-supporting under tunnel excavation conditions. And the margin between the planned tunnel crown and the seafloor above the protective layer of rock shielding the tunnel from direct contact with the ocean was in places barely 100 meters thick. In tunneling terms, that is a razor's edge. The engineering response to this geological reality was to design not one tunnel, but a system of 3 parallel bores, all driven simultaneously from both ends. At the center of the system, a pilot tunnel smaller, driven ahead of the main bores, would serve as the geological advance guard. Every meter of pilot tunnel driven would probe the rock before the larger, structurally more demanding main railway bores reached the same location. On either side of the pilot tunnel, at a horizontal distance of approximately 30 meters, the 2 main railway tubes would follow. The pilot bore would not only detect problems in advance, it would provide drainage, establish ventilation connections, allow installation of rock support systems from multiple directions, and serve as an emergency evacuation route for workers in the event of a crisis in the main bores. This was not redundancy for comfort. This was a survival architecture built into the design of the tunnel system from the very beginning. Then came the actual drilling, teams working from the Honshu side from the Aomori Prefecture portal at Tapi. Saki drove south to north through the coastal cliffs and out under the strait. Teams working from the Hokkaido side from the Fukushima Cho portal drove north to south. The 2 sets of headings converged over 23 kilometers of ocean, aiming to meet with an alignment tolerance measured in centimeters. The surveying required to maintain that accuracy across that distance underground, with no direct line of sight between the 2 advancing headings, was itself an achievement of extraordinary precision. Gyroscopic survey instruments, precise leveling loops, constant cross, checks against surface survey control, points every measurement mattered because a misalignment discovered deep under the ocean is not correctable without catastrophic cost. The drilling cycle at each working phase followed a precise and repetitive sequence. Surveyors marked the blast pattern on the face, the arrangement of holes to be drilled, each one positioned to direct the energy of the explosive charge most efficiently into the rock. Drilling crews mounted on hydraulic jumbos, large tracked vehicles carrying multiple hydraulic drill arms simultaneously, drove the boreholes into the face, depending on the rock type and the diameter of the tunnel being driven. Each blast round might require between 30 and 80 individual drill holes, each drilled to a depth of between 1 and 3 meters. Every hole mattered. The diameter, the angle, the depth, the precise position, all of it affected how cleanly the rock broke, how much of it was shattered into manageable pieces versus crushed into fine dust. When the drilling was complete, the shot firers loaded the holes with explosive charges, carefully calculated loads, sequenced to fire in precisely timed intervals using detonators, creating a controlled cascade of blasts that excavated the face without generating shockwaves severe enough to destabilize the already fractured surrounding rock. Workers evacuated the heading, the tunnel filled with smoke, dust, and the sharp smell of spent explosive. Ventilation fans ran at maximum power to clear the fumes. Then the mucking crews moved in with loaders and rail cars, scooping up the broken rock, the muck, and hauling it back along the tunnel to the portal where it was deposited in the growing spoil heaps outside. Then came support. This was not optional. In the Seikan Tunnel's geology, unsupported rock above and beside a freshly blasted opening would begin to loosen and fall within hours. Steel arch supports heavy curved steel sections bolted together were erected across the tunnel profile, one arch per blast round advance, providing immediate structural resistance to the rock load. Wire mesh was hung between the arches to catch smaller falling fragments. Then shotcrete, wet concrete sprayed under pressure from a nozzle, was applied in layers to the entire tunnel walls, crown, and arch flanges, encasing the steel in a rigid composite lining that redistributed the load and sealed the surface against air and water. Rock bolts, long steel rods driven deep into the surrounding rock and anchored with resin or cement grout, were installed in systematic patterns to stitch the rock mass together, preventing the progressive unraveling of fracture zones that could lead to collapse. Finally, systematic probe boreholes, long-angled drill holes driven ahead of and around the working face, were used to detect water-bearing zones before the main advance reached them, giving the grouting teams time to seal the fractures with injected cement. This cycle survey, drill, blast, muck, support, probe, grout, was the heartbeat of the Seikan Tunnel construction, repeated thousands of times, repeated in conditions that included water dripping from every surface, temperatures hovering around 20 degrees Celsius with 100% humidity so that sweat never evaporated, noise levels from drills and fans and machinery so intense that face-to-face conversation was impoverished. And then the water came. In 1969, the pilot tunnel's advancing face in the undersea section encountered a fault zone more heavily saturated than the probes had indicated. Water inrushed at a rate that rapidly overwhelmed the drainage system. Pumps were overwhelmed. Workers retreated. Emergency pumping equipment was rushed underground. The advance was halted while grout injections sealed the fracture zone from within, and additional drainage sumps were excavated to manage the flow. It took weeks. The tunnel survived, and the engineers learned probe harder, grout more aggressively. Never assume the geology ahead is as good as the geology around you. But the learning was not finished. On May 6, 1976, in the deepest and most water-saturated section of the undersea pilot tunnel, a working face broke into a fault zone of extraordinary scale. The rock simply opened. Seawater at high pressure poured into the tunnel in quantities that no installed pump system could match. Approximately 70 million liters of water flooded the lower sections of the tunnel over the course of several days. This was not a seep. This was not a manageable inflow. This was the sea trying to reclaim the space that human beings had carved out of its floor. Workers evacuated the flooded sections. All non-essential personnel were withdrawn from the undersea zone. Emergency pump trains, additional pumping units mounted on rail cars, and rushed into the tunnel, ran at full capacity around the clock. Dozens of grout boreholes were drilled from inside the tunnel into the surrounding rock, injecting grout under enormous pressure in an attempt to build a barrier between the fractured zone and the tunnel opening. The operation continued for approximately 6 months. 6 months of continuous emergency response, underground, beneath the Tsugaru Strait, in conditions that no tunnel worker should ever have to face. The project was not abandoned. That choice to continue, to solve, to not retreat, is perhaps the defining decision in the entire 24-year history of the Seikan Tunnel. The flooding of 1976 was brought under control. The grouting worked, the water was pumped out, the face was secured, the advance resumed, and the lessons of May 1976 were incorporated into every subsequent meter of tunnel driven through the undersea section, extended probe drilling distances. Increased grout volume requirements, redundant pumping capacity installed permanently throughout the system. With the pilot tunnel complete, the moment its two headings broke through to each other, the holing through, celebrated with ceremony by the workers who had driven toward each other in darkness for years, the main railway bores could now advance through geology that had already been probed, drained, and partially grouted. The main tubes were larger, required heavier support systems, and were structurally more demanding than the pilot bore. But they advanced with the confidence that comes from having already crossed the same ground once before. The main bore construction required all the same systems as the pilot tunnel: heavier steel arches, thicker shotcrete layers, denser rock bolt patterns, more powerful ventilation, larger muck-hauling trains, heavier grouting equipment, and running parallel to all of it. Constantly the monitoring systems that watched the ground, the water, and the structure for any sign of distress. The track installation in the Seikan Tunnel was not a conventional railway track job. The environment, permanent high humidity, groundwater flowing along drainage channels in the invert, proximity to the sea, the dynamic forces of high-speed rail traffic demanded a track system specifically engineered for these conditions. A concrete slab track system was installed throughout the undersea section, eliminating the ballast that would have been impossible to maintain in the wet, confined environment of a deep submarine tunnel. The slab is cast in place on the tunnel invert, incorporating drainage channels running along both sides to collect water and direct it to pump sumps. The rail fastening systems are resilient, vibration absorbing, and designed to hold gauge precisely under repeated loading from trains crossing at high speed. The expansion management at the transitions between the subsea section and the land sections accounts for the differential movement between rock at depth, which is thermally stable and barely moves, and the approach structures on either side. The electrical systems running through the Seikan Tunnel constitute an entire infrastructure project in their own right. The overhead catenary, the wire from which trains draw their traction power, is suspended from brackets attached directly to the tunnel lining, installed with the precision required to maintain constant contact with the pantographs of trains passing beneath at 260 kilometers per HR. The power supply substations that feed the catenary are located in purpose-built underground rooms excavated from the rock beside the main tunnel at intervals along the route. The signaling systems, the electronic brain of the railway, managing the movement of trains through the tunnel and ensuring that no two trains occupy the same section of track simultaneously, are housed in climate-controlled equipment rooms along the tunnel wall, connected by fiber optic data cables. The telecommunications systems, the emergency broadcasting systems, the CCTV systems, the fire detection systems that continuously sample the tunnel atmosphere for smoke and elevated temperatures, all of these run through 53.85 kilometers of carefully managed cable routes, junction boxes, and equipment enclosures, serving a structure where a fire or an emergency is not a situation that outside emergency services can reach quickly. Then there are the two underground stations, Tapi, Keitei, on the Honshu side of the undersea section, Yoshioka, Keitei, on the Hokkaido side, both carved directly into the rock of the Tsugaru Strait seafloor, accessible from the main tunnel by cross passages. These stations were constructed primarily as safety refuges, designed to receive the passengers and crew of a disabled train in the undersea section, providing them with a safe, ventilated provision space in which to wait for rescue trains to arrive. Each station includes a platform zone running alongside the main tunnel, passenger waiting areas with seating capacity, for several hundred people, empattic systems separate from the main tunnel ventilation, communication systems with direct connections to both the surface operations center. They are extraordinary spaces, fully equipped rooms, lit by fluorescent lights, maintained at habitable temperature and humidity, sitting in silence and stillness, hundreds of meters below the seafloor, waiting for an emergency that, by the grace of the engineering around them, has so far never fully materialized. The Seikan Tunnel opened for commercial railway service on the 13th of March 1988. For the first time in history, it was possible to travel between the Japanese islands of Honshu and Hokkaido without boarding a vessel and crossing the sea. Passengers could sit in a train car, cross under the Tsugaru Strait, and emerge on the other side without ever being aware of the weather above, without ever being at the mercy of the typhoons that had made the crossing dangerous for so long. The tunnel worked after 24 years, and approximately 690 billion yen, and 34 lives, and 2 catastrophic flooding events, and an almost unimaginable accumulation of human effort. The tunnel worked then, on the 26th of March, 2016, the Hokkaido Shinkansen running through the Seikan Tunnel for the first time. The upgrade to Shinkansen operations had required years of additional work inside the tunnel. New slab track sections, upgraded catenary and power supply systems, new signaling and train control equipment calibrated for speeds 3 times faster than the original tunnel had been designed to carry, and new rolling stock specifically developed for the combined demands of high-speed operation. When the first Shinkansen entered the Seikan Tunnel's portals and accelerated into the darkness beneath the Tsugaru Strait, it was traveling through a passage that had been paid for with 24 years of human determination and the lives of 34 workers who would never see it completed. Most passengers today do not think about any of this. They take their seats, they open their laptops or their phones, they feel the train accelerate as it enters the tunnel portal. They watch the tunnel walls begin to blur. They do not see the 34 workers whose names are recorded in the memorial near the portal, who gave their lives so that this crossing could exist. They do not see the probe boreholes drilled ahead of every single blast round the quiet, unspectacular act of caution that prevented 100 potential catastrophes in the undersea section. They do not see the grout injections pumped under enormous pressure into fractured rock that wanted nothing more than to collapse into the space being carved through it. They do not see the 6 months of emergency pumping in 1976 when approximately 70 million liters of the Tsugaru Strait flooded into the tunnel and the workers who were there refused to abandon what they had built. They do not see the underground stations carved into the sea floor, fully equipped and quietly waiting, populated only by maintenance personnel and the distant hum of the ventilation fans that keep them habitable. They do not see the monitoring systems running along every meter of the tunnel wall, the sensors measuring water inflow and rock deformation and air quality and temperature and vibration, the data flowing in real time to the operations center, where engineers watch the tunnel's vital signs. 24 hours a day, 7 days a week, 365 days a year. They do not see the drainage channels carrying groundwater silently to the pump sumps at every low point. The pumps running continuously, the water lifted back toward the surface and disposed of the quiet, ceaseless labor of keeping the ocean out of the space that human beings carved through its floor and chose to call a railway. What passengers see is the window going dark, the tunnel walls strobing past at 260 kilometers per HR. And then, after roughly 30 minutes beneath the sea, a rectangle of gray light ahead. The tunnel portal, Hokkaido, a new island, a new place, connected to the rest of Japan, not by luck of weather and the courage of ferry crews, but by the permanence of rock and concrete and steel and the irreversible fact of what human beings built here over 24 years of extraordinary effort. This was not just engineering. This was a response to grief. It was a promise made to the 1,150 people who died crossing the strait in 1954 that no one would ever have to die crossing it again. Not because the weather had become gentler, not because the sea had become kinder, but because the passage beneath the weather and beneath the sea had been built. And it would be there always, regardless of what happened above. Every drill hole mattered, every grout injection mattered, every steel arch mattered. Every one of the 34 workers who lost their lives building it mattered, and matters still. Without it, thousands more crossings at the mercy of the Tsugaru Strait With it, a passage so deep beneath the storms that the weather above is simply irrelevant. The Chueomaru sank because there was no other way. There is another way now. Human beings built it. Not machines operating autonomously in the darkness. Human beings with drills and explosives and pumps and grout and surveying instruments and steel arches and concrete. In the dark, in the wet, in the noise and the heat and the extraordinary physical difficulty of creating a space, they built a passage under the ocean because people were dying without one, and they finished it. If you found this story as extraordinary as we did, please subscribe to the channel and leave a comment below. Tell us which engineering megaproject we should cover next. There are extraordinary things waiting to be explained. Thank you for watching.